Without further ado, let's begin this evening program by inviting our distinguished dignitaries to grace the virtual stage. Dr. Amit Singhal, sir, HOD CSE and coordinator of this FDP. Dr. BC Sharma, sir, Director RKGIT. Dr. Kusum Yadav, professor at the University of Hill Kingdom of Saudi Arabia, and today's guest of honor. Dr. R.K. Yadav, Dean Academics, RKGIT, Dr. Pawan Kumar Goyal, Associate Professor and Co-Coordinator of this FDP. We extend a warm virtual welcome to all of you. To begin the proceedings, may I now invite Dr. Amit Singhal, sir, Head of the Department of Computer Science and Engineering and Co-Coordinator of this FDP, to provide us with an overview of this faculty development program.
Thank you, Vartika ma'am. Am I audible?
Yes, sir.
Yes, sir, you are audible.
Thank you. So, good evening, everyone. Honorable Vice Chairman Sri Akshat Goyal ji in absentia, Director sir, Dr. BC Sharma sir, Dean Academics Dr. R.K. Yadav sir, our esteemed guest of honor, Dr. Kusum Yadav from the University of Hail Kingdom of Saudi Arabia, all deans, HODs, faculty members and dear participants. It is both an honor and privilege to welcome you all for this inaugural ceremony of this 1 week ATAL FDP on the theme Quantum Machine Learning, Bridging the Gap Between Quantum Computing, organized by the Department of Computer Science and Engineering, sponsored by AICTE New Delhi. On behalf of the entire department of CSE at Rajkumar Goyal Institute of Technology, Ghaziabad, and my personal behalf, I, Dr. Amit Singhal, extend a warm and sincere welcome to all of you. This program is designed not only to enhance your knowledge, but also to inspire and encourage the exchange of innovative ideas in the ever-evolving field of quantum computing. So our department's mission is to deliver top-tier technical education and promote cutting-edge research, empowering the next generation of engineers to lead global technological advancement. This FDP equips educators with the latest teaching strategies, tools, and technologies, fostering the integration of advanced pedagogical approaches. This FDP aims to provide in-depth practical insight into the quantum computing. Over the next 6 days, you will be exposed to the exciting challenges and boundless opportunities this field offers. With the ability to solve complex problems that were once considered unconquerable, quantum computing has a potential to reshape industries from cryptography to artificial intelligence and beyond. So to all the participants, I encourage you to actively engage throughout this program, ask questions, participate in discussions, and interact with your peers. I am confident that over the next 6 days, you will find yourself enriched with valuable knowledge, new perspectives, and an expanded network. So I wish you all the rewarding, insightful, and enriching experience throughout this program. Thank you. Over to you, ma'am.
Thank you so much, Dr. Singhal, sir, for sharing the vision and objective of this FDP. Now, I would like to invite our esteemed director, sir, Dr. BC Sharma, sir, to deliver the welcome address.
Is I audible?
Yes, sir, you
Yes,
are
sir.
audible.
Thank you. First of all, on behalf of the Rajkumar Goyal Institute of Technology, I heartily convey my sincere thanks to the AICTE for giving us this online ATAL FDP on quantum. Right? My heartily welcome to Dr. Kusum Yadav for accepting our invitation through Dr. Amit and Dr. Pawan on such a short notice. Getting such type of the guests on this platform is really an honor for each participant. I heartily welcome all the participants because for the first time AICT is doing this trial in the evening hours when we reach home and needs because during the daytime AICT considers that we all are busy in our day-to-day academic activities, and now minimum for 3 hours we will be I request each one of you to manage your home schedule in such a way that you should attend this. Amit has already explained you regarding the uh, content that will be covered in next 6 days, and I hope that this content will definitely be delivered or shared with the student in the coming classes, those who will take this subject in their uh, in actually future. And purpose of the FDP is also uh, same, that those who are doing research in this area will get the advanced knowledge, or the advanced topics will be covered in this, plus the industry requirements in these subjects will definitely help each one of you in the actually coming semesters or the academic sessions. So without wasting time, I convey my sincere uh, thanks to my organizer, my team of RKGIT, who is working day and night in organizing FDPs online and offline, because we during the last 1 year, we have organized so many reputed FDPs either through AICT, through NITTR, even many FDPs are organized um, in-house also. Even today, when we get an opportunity, we have started one Python FDP for my faculty so that they will be in line with the requirement of the industry, that how they can provoke the students on the Python coding that will help each one of us. So my best wishes to each one of you, and I hope that in these 6 days you will definitely learn a lot on this quantum mechanics. Thank you very much, Amit.
Thank you, Dr. Sharma sir, for your inspiring words and for setting the tone for this event. Today's inaugural ceremony guest of honor is Dr. Kusum Yadav, who holds the position of Associate Professor at College of Computer Science and Engineering, University of Hale, Kingdom of Saudi Arabia. With an extensive academic background spanning over 2 decades, she has imparted knowledge in computer science at both graduate as well as postgraduate levels in India and Kingdom of Saudi Arabia. Dr. Yadav, an accomplished researcher, has more than 85 publications in esteemed international journals and conferences, including books, chapters, and papers. Her innovative pursuits extend to intellectual property rights, evident in her publication of 18 patents under IPR India, alongside 3 granted patents, 2 UK granted patents, 2 Canadian patents, and 2 Australian patents. Demonstrating her expertise, Dr. Yadav has delivered numerous expert lectures, chaired technical sessions, and held board memberships in reputable international and Scopus Index journals. Active in cutting-edge fields like blockchain, artificial intelligence, the Internet of Things, big data, and cybersecurity. She is also involved in professional societies like IEEE, ACM, and ISTE. Dr. Yadav's multidisciplinary contribution have established her as a distinguished and influential figure in academics and research. It's now my privilege to invite our distinguished guest of honor, Dr. Kusum Yadav, professor at University of Hale, Kingdom of Saudi Arabia, to share her thoughts and insights. We all welcome you, ma'am.
Good evening, everyone. And I'm so honored that I have been, literally called for this FDP. This is my good luck that Amit sir contacted me for as a resource person and as a guest of honor. I will try my level best to give my bit of knowledge, whatever I have acquired, and my input in this FDP. For being an Indian, like working in a out of India university, we all, we are habitual of working in nights. like all our workshops, all our what do you say, whatever is, except classes, everything is after 5 o'clock. So today, honestly, I was shocked that we are going to adopt the same culture in India also. So welcome people on the welcome in the club of night birds. We will be working in late nights also as well, to develop ourselves so that we can give our best, whatever we are learning. We can give the best to our students, we can deliver the best product, we can give our input to the society. Because at the end of day, as a teacher, it is our responsibility to produce the person who is responsible, who is ethically right, and most important, being an Indian. Because I heard in out of India, especially in Middle East, we are not counted as Indians. We are counted like, if they're calling me, they will be calling me Hindi. They will not call me Hindu, they will call me Hindi. And they said, Hindis, you are technically so sound. Yes, because we actually work hard on us and on our students. So I am so honored. Again, thank you very much for Rajkumar Goyal Institute for inviting me for this FDP. Thanks a ton. Thank you, the management. Thank you, Amit sir. Thank you, Pawan sir. And best of luck for this FDP. Thank you.
Thank you, ma'am.
Thank you, ma'am. Thank you, Dr. Yadav, ma'am, for your enriching and thought-provoking address. We are fortunate to have with us Dr. R.K. Yadav, sir, Dean Academics, RKGIT. May I now invite Dr. Yadav, sir, to address the gathering.
Director Dr. B.C. Sharma, sir, HOD of Department Dr. Amit Singhal, faculty members, esteemed participants, faculty members, and honorable speakers. On behalf of Department of Computer Science and Engineering at Rajkumar College of Technology, Ghaziabad, I, Dr. R.K. Yadav, truly delighted to address you on this 6-day faculty development program on quantum computing learning, bridging the gap between quantum computing and AI. This program, under the prestigious AICT ATAL scheme, promises to be a remarkable opportunity to explore the intersection of two of the most transformative fields in modern technologies, quantum computing and artificial intelligence. We are fortunate to have expert speakers and trainers who will guide us through the complexity of these technologies, helping us bridge the knowledge gap between theory and practices. I encourage all participants to encourage actively, ask questions, and collaborate to make the most of this wonderful learning experience and a good networking. I would like to express my sincere gratitude to AICT for their support and to each of you for being a part of this program. I am confident that the insight gained during this FDP will empower us to contribute meaningful to the evolving world of technology. I wish all the best for all the participants for the truthful and the productive FDP, and best wishes to Department of Computer Science and Dr. Amit Singhal and his team for arranging a wonderful FDP. Thank you, Amit. Thank you, Varnika. Over to Amit.
Thank you, ma'am. Thank you, sir.
Thank you, Dr. Yadav, sir, for your encouraging words and valuable insights. Now, as we approach the conclusion of this inaugural session, it is time to express a heartfelt gratitude to everyone who has contributed to making this event possible. For this, may I now invite Dr. Pawan Kumar Goyal, Associate Professor and Co-Coordinator of this FDP, to deliver the vote of thanks.
Very good evening, everyone. On behalf of the organizing committee, it is my privilege to deliver the vote of thanks for this AICT-sponsored ATAL FDP on quantum machine learning, bridging the gap between quantum computing and AI. First and foremost, I would like to express my heartfelt gratitude to Chairman of AICT and Director of AICT ATAL Academy for considering our FDP proposal. I extend my sincere thanks to our institutional management, including the Chairman Sir and Vice Chairman Sir in absentia, and a special thanks to all the dignitaries such as Advisor Sir and Executive Director Sir. I am deeply gratitude to Dr. B.C. Sharma Sir, Director of RKGIT, for his invaluable support and guidance for this event. A special thanks to Dr. Kusum Yadav, our esteemed guest of honor and associate professor at the University of Hail Kingdom of Saudi Arabia, for gracing the occasion with her presence and insightful contributions. I would also like to thank to Dr. R.K. Yadav sir, Dean Academics, as well as all the deans and head of departments of RKZIT for their active participation and encouragement. My special gratitude to Dr. Amit Singhal sir, Head Department of CSE, for his relentless support in organizing this FDP. Finally, I extend my warm thanks to all the participants, faculty members, technical and organizing team who are constantly working at the back end to make this FDP grand success. Thank you.
Thank you, sir. Thank you all for joining this inaugural ceremony.
Thank you. Thank you, Dr. Goyal
Thank
sir,
you.
for your kind words of appreciation. Now, with this, we conclude the inaugural session of AICT-sponsored ATAL FDP. We sincerely thank all the dignitaries, guests, and participants for their presence and support. We look forward to your active participation in upcoming technical session over the week. Thank you and have a great evening. So we are starting the program with the session 1 titled Quantum Computing and Machine Learning Fundamentals. This session will serve as a stepping stone into the exciting world of quantum computing and its integration with machine learning, laying the groundwork for the session to come. Our distinguished speaker for this session is Professor Dr. Pradeep Kumar, a highly respected academic and researcher. He is Distinguished Professor in Department of Computer Science and Application and Director at IT Cell at Kurukshetra University, with over 27 years of teaching experience in undergraduate and postgraduate programs. He holds a PhD in Computer Science and Application, along with MSc degree in Computer Science and Statistics and Operational Research. Dr. Kumar specializes in subjects like design and analysis of algorithm, machine learning, programming language, data structures, and cloud computing. An accomplished academic, he has authored over 80 research papers in SCI, Scopus, and WS Index Journal, published 2 patents, and guided numerous PhD and MTech students. With extensive involvement in organizing workshops, refresher courses, and conferences, Dr. Kumar has made significant contribution to the academic and professional development of this field. His research interests span optimization, network routing, anonymization, privacy preservation, and sentiment analysis. And he actively participates in institutional role as a board member, selection committee expert, and a resource person. Before we begin, a gentle reminder to all the participants, kindly ensure your microphones are muted during the session to avoid any disruptions. And if you have any question, please use the chat feature and we will address them during question and answer segment. Without further ado, let us warmly welcome Professor Pradeep Kumar to take us through the fundamentals of quantum computing and machine learning. Over to you, Dr. Kumar, sir.
Thank you, ma'am. Thank you. Thanks a lot. Actually, I'm unable to switch on my camera because somehow it is rotated. Let me show it to you. Somehow it is not showing in the correct way. So I will switch this off. I hope it is all right to
Yes, sir.
switch
Yes.
off my
Okay,
camera.
sir. Okay, sir. No problem.
Fine, fine. Thank you. Thank you.
Please, sir. Please continue.
Okay, thank you. So let me share my content first. So I hope my screen is visible to every participant.
Yes, sir.
Fine. Thank you. Thank you. So I will be dealing with this topic, that is Introduction to Quantum Computing and Machine Learning. Okay. But before starting this, what we mean by quantum computing or what we mean by machine learning and how they can be integrated. First, let us try to delve into machine learning. Okay. I think machine learning, most of you are already familiar. Okay. So let me ask a few questions with reference to machine learning. Okay. So I hope participant will participate in this and will answer my questions. Okay. So what do you think? why the accuracy of machine learning is not 100%. It is maybe 80% in some cases 85%, some cases 50%. Why so? Why the accuracy of the answers in case of machine learning is not 100%? What could be the reasons behind it? Can any of the participants answer this question? I repeat my question. My question is, whenever you apply a machine learning model to predict something, the accuracy of that particular model, whatever model you are applying, the accuracy is not 100%. It is maybe 50%, maybe 50 to 90%. And if the model is very good and the database is also very good, maybe up to 95%, not 100%. What is the reason behind that? Can any of the participants say something about this? Okay. I'm not sure that whether they are able to mute themselves or not. So let me answer that question. Okay. So answer for that question is.
Sir, excuse me. Good evening, sir.
Good evening.
This is
Yes,
Manjula.
please go ahead.
So as far as machine learning is concerned, there we have to give, to predict anything, we need to give features in the form of handcrafted features.
Exactly.
So it may be some reduction in the accuracy level. As far as the quantum computing is concerned, it take almost closest to the very good accuracy. So that we are moving to from machine learning to quantum computing. Before that, we have deep learning. I think it may be correct. Thank you, sir. Thank
that
you,
is
sir.
correct. What Dr. S. Manjula has told us that basically when we are applying machine learning, in case of machine learning, the basic issue is when we are using some features, features for maybe implementing a model, we are not using 100% of the features, we are reducing some features, and after reducing the feature, we are applying the machine learning. And that's why there might be some scenarios in which a particular maybe a particular parameter is missed and which was required for that. Okay. In case of machine learning and in case of standard computers, that computers which we are using till date, okay, the problem is this, that whenever you are using current stage computers, in that case there are only 2 bits, that is 0 and 1. Okay, but between 0 and 1 there are number of states as well. Okay, so in case of quantum computing, the basic difference is that we are not only considering only 2 states, that is 0 and 1, rather we are going to consider a number of states, that is all the possible states that we are having. And exactly in the same scenario, suppose we are applying a machine learning model, okay, and we are trying to predict something for the future. Okay, the problem will be this, that if you are trying to predict something which is not in our database, for example, in your database there are cats, there are dogs, and there are some other animals. Okay, let us assume tiger is not there in your database, and in future you are willing to predict that you are giving the input as the tiger. Because the feature of the tiger are not there in your database, the problem will be that it is not able to come to conclusion, but whether it is a cat, whether it is a dog, or whatever it is. Okay, because features are not matching. That means the input is missing in the database. Okay, while in case of quantum computing, whenever we will be trying to implement this, we will be considering all the possible cases, and accordingly the accuracy will be much more higher in case of quantum computing as compared to machine learning that we are using till today. Okay, so that's why quantum computing, as and when it is being used professionally, in that case it will what I think is it will change whole sum of the machine learning. The accuracy of the machine learning and the implementation of AI will be of very good quality and will be having very high accuracy. Okay, so that's why quantum computing is very important for implementing the AI features as well as machine learning features. Okay, so that's why I will be focusing more on quantum computing and I will be focusing very less on machine learning. Okay, so let us start with what is quantum computing. So basically, when we talk about quantum computing, okay, so basically, as it is written over there, quantum computing is a science based on principles of information theory and quantum mechanics. Okay, so basically, 2 things we are intermixing. What are those two things? One is the information theory. Okay, information theory is basically the theory that we are studying till now. That is, we are storing some data, we are getting some information, we are on the basis of that information we are taking some action. So exactly same type of scenario will be there in the quantum computing. We will be trying to store some information, we will be trying to retrieve that information. And other important aspect in case of quantum computing is that we will be using quantum mechanics. That is, we will be using the features of quantum mechanics. Now the question arises whether we should be an expert of quantum physics, or you can say quantum mechanics. The answer is yes and no both. Okay, you need not to be expert, but you should have at least some basic knowledge of the quantum mechanics that we will be trying to discuss in this particular technical session, right? If we go ahead. Basically, this quantum computing, it is basically a structure which defines the universal language to efficiently write quantum algorithms. We will try to write some algorithm which will be termed as quantum algorithm. Although in this particular, you can say session, we won't be focusing on the quantum algorithm, because if we focus on the quantum algorithm, actually we have to stick to the quantum algorithm and it will take a lot of time. So I will not be touching upon the quantum algorithms. A little bit about quantum algorithms are particular algorithms that exploit some properties deriving from quantum mechanics. Okay, till now, whatever algorithm you are using, those algorithms are based on maybe data, whatever data you are storing in terms of integer or whatever it is. Okay, so that data will remain as it is. The only difference will be the operation that you will be applying, that will be based on quantum mechanics, and the input, that is input till now is in terms of bits. Okay, you are inputting the data in terms of bits, your computer is storing in terms of bits. But in quantum mechanics, you will be storing data not in terms of bit, but in terms of a different structure which will be termed as qubit. Okay, so that will be the thing. Further, if we talk about that, in order to work, quantum algorithms therefore need to operate through computers capable of manipulating objects in which the quantum is sufficiently manifest. Okay, so that is the basic idea about what we mean by quantum computing. So if we combine all these features, then we can define basically the quantum computer. So any particular computer which is having all those features will be termed as quantum computers. Okay, now let us talk a bit more about quantum mechanics. Okay, now the question is, as I told you, for understanding quantum computing, whether we should be an expert, no, it is not necessary. Okay, but at least basic idea should be there, so that we will be looking upon. Okay, and the first and the foremost and the most important principle in case of quantum computing is superposition principle. Okay, now what we mean by superposition principle, just look at this diagram. Okay, so are you able to read this? If you can answer this, are you able to read whatever is written over there? If you can read this, if any of you can tell me what is written in this. Either you can type your answer or you can speak out. If you can say
Alive.
this. Yeah. Is there anything else as well? Actually, to be exact, there are two. Yes, yeah. Vineet Srivastav, you are right. So there are two answers in this case. One is alive, other is dead. Okay. So if you focus on this particular text, you have got two different things. That is, one is alive, other is text. Okay, dead, I'm sorry. Okay, so the thing is, both the things are superimposed on each other, and this position is termed as superposition state. Okay, and in quantum mechanics, we are considering these states as well. Till now, the computers that we are using till date, we are using actually the classical mechanics. In case of classical mechanics, you are using only two states, as with reference to computer I am talking about. That is, you are using either zero state, you are using either one state. Okay, and you are not using any other state. But in case of quantum mechanics, there is a principle which is termed as quantum superposition principle, and what it states, if you can mute please. Yeah, so in the
Sir,
quantum
kindly
mechanics,
mute all the participants.
yeah, I think I can continue.
Okay, sir.
Avan sir?
Thank you. Thank you, sir. Thank
Please,
you.
sir. Please.
Yeah, thank you. So as we were discussing this quantum superposition principle, so what we are saying in this principle, in the quantum mechanical design, objects don't manifest only a single state, but all the possible states. That is very important with reference to machine learning. That is all the possible states that they can assume at the same time. It's significantly disturbed. The superposition state collapses and object is forced to assume a classical state. Now, what it is trying to say? It is trying to say in the first part, it is saying superposition principle is that which is considering all the possible states. Now, in case of machine learning, what we were lacking? We were lacking that we were having a database in which only a limited database was there. Okay. And we were just estimating that if a tiger is to be estimated, we might say that it is a cat because most of the features of the tiger and cat, maybe look wise or something like that, they may match. So we may incorrectly say that it is a tiger. But if you are using quantum computing, then there are bright chances that you will say that you are not knowing about that data because that state is not matching with the superposition principle. That state is missing. Okay. I'm not saying that this will exactly happen in the same manner, but it might happen. Okay. So the accuracy of the machine learning model will be comparatively very high if we are using quantum mechanics principle. Other thing that we are saying in this particular principle, when we will be trying to implement quantum superposition principle, obviously, if we have to store the data only in terms of 0 and 1, and we are trying to use quantum mechanics, and we are trying to store the data still in 0 and 1, we are not using all the states. In that case, we will be looking upon this thing that how the superposition states will be collapsing into either 0 state or 1 state. For example, if you look at this particular picture, in this case, this is alive cat, this is dead cat. Okay, so depending on, you have to say either you have to either superimpose, or you can say you have to say either this cat, if you are looking at this particular point, for example, this is the cutoff point. Okay, so if you are looking at this point, then clearly it should be said that it is basically alive. If you are pointing on this particular point, you have to clearly state that it is dead. But if the data is lying something in between, okay, in that case, what will happen? Okay, so that type of scenario we have to look upon in case of quantum mechanics, right? Second principle that we use in case of quantum mechanics is measurement. Okay, now what we mean by this principle, that is measurement. Now, with the term observation or measurement of a quantum state, we mean that process which through spatial instrument quantifies a certain quantity belonging to a microscopic object. Meaning is this measurement actually can be seen as a sort of intrusion of the macroscopic world into the microscopic world. So what we are trying to say, that is, we are trying to convert a macroscopic world into a microscopic world with the help of measurement, although it is quite difficult to do. But what quantum mechanics says exactly this thing. Okay, further, it inevitably perturbs the quantum state of the matter, causing the state to collapse in a classical state, the only category of state that we human of macroscopic world can recognize. Now, what it is trying to say? It is trying to say exactly the same thing that we were discussing in superposition type of thing. That is, that suppose we have to measure the data only in terms of 0 and 1. Okay, so we have to convert the microscopic instructions, or you can say the microscopic information, into a macroscopic information. That is the information that was in between. That is, neither the cat was both dead in a particular section and alive as well. Okay, so we have to identify whether we have to put that into dead cat or whether we have to put into the alive cat. Okay, so that is what we know as measurement, right? This was the first principle, which was comprising of two different things, that is superposition and measurement. Then the second principle of quantum mechanics is entanglement. Okay, now entanglement is altogether a different principle, which can't be thought of in case of classical mechanics. Okay, in case of classical mechanics, what we say that suppose we toss a coin. Okay, so in that case, the answer will be head or tail, right? Then we toss same coin again, or let us say we are tossing another coin. Okay, then can you tell if suppose the output of the first coin was head? Okay, can you estimate what will be the output of the second coin? Answer is strictly no, because if both the coins are unbiased, then we can't guarantee that what will be the outcome of the second coin. It may be head, it may be tail. Okay, so that means those two events or those two coins are not dependent on each other. They are independent. It might be possible that you are tossing 10 coins. It is possible all the 10 may come head, all the 10 may be tail, some 6 may be tail, 4 may be head, whatever it is. Okay, we are not knowing this thing whether that will happen or not. But what this quantum entanglement says, it says something different. Okay, it says that if we are tossing two coin, okay, and in which we are applying the quantum entanglement principle. Okay, and if suppose first one is head, then we can predict that whether the second will come as head or tail. Okay, depending on what type of operator we are applying. So that is what we know as entanglement. Entanglement means that is the two objects, however far they are. For example, I am tossing a coin at this place and you are tossing a coin at your place. Okay, and suppose we are two friends. Okay, in that case, I have tossed the coin, head is come. I can directly predict that your coin will also be head or your coin will be tail. Okay, so that is what we know as quantum entanglement. We will just go through this. Okay, so what it is saying, phenomena closely related to the superposition principle and the collapse of the quantum state into a classical state after a measurement. This principle states that there is a particular condition that can bind two quantum particles regardless of the distance. This link is such that the observation of one of the two particles is also reflected on the other. Okay, conditioning conditioning the classical state in which it collapses. Okay, exactly the same meaning that I have told you, that is being told by this particular quantum entanglement, right? We shift our attention to the third principle, and the third principle in quantum mechanics is tunneling effect. Okay, now what we mean by tunneling effect? When we talk about classical physics, just focus on this diagram. Okay, in case of classical physics, suppose a person is going and this is maybe a wall is there, or maybe you are throwing a ball, whatever it is, whatever you can assume. Okay, so in that case, suppose a person is trying to cross this wall directly without maybe going above the wall or whatever it is trying to directly go through the wall. Okay, so obviously this will happen. Okay, so but if you are using quantum physics or if you are using quantum mechanics says that tunneling effect is there, and tunneling effect states that when a person is moving from this place to this place, it can directly go through the wall. Okay, so that is another principle that is used in quantum mechanics. We will just go through this. Okay, what it is stating, by definition, we speak of tunneling effect when a particle manages to make a transition that is not normally possible according to the set of classical mechanics as we are stating in this. In simple words, this principle states that under certain circumstances, a quantum particle can cross energy barriers, just like it is using this energy barrier, as if a ball could be able to pass through a wall instead of bouncing against it. Okay, so that is, I'm sorry, that is what we know as tunneling effect. Now, these are some of the examples of, you can say, quantum revolution. Okay, so these are some of the examples with reference to first quantum revolution. Okay, now, although the quantum revolution has not taken place as yet, we can't say that quantum revolution has taken place, but still, till date, whatever has happened in the quantum computing, we can say that some type of revolution has occurred, and these are some of the examples of the first quantum revolution. But it is saying, for example, laser light is one of the quantum revolution. Another is transistor, other is touch screen, other is GPS. Okay, now how it is possible? Now what we are saying, in case of GPS, okay, there are boundaries between countries, maybe, but still GPS is able to search for everything. It is able to tell whether traffic will be there, whether these type of things will be there. So it is actually using basically the real-time scenario. Okay, And quantum mechanics is exactly saying the same thing, that it is using the real-time scenario. Quantum computing uses real-time scenario. It is not using basically 0-1 type of scenario. Okay, same is case with the maybe transistors. Okay, the frequency of transistors is irrespective of the boundaries or these type of things. So these are some of the examples of, you can say, quantum revolution. Okay, so that is bit about this. Uh, I think I have already explained this, that despite their strange nature, over the years and more experiment have validated the theory of this thing. So these are some examples. So I think I don't need to read this. Okay. This phase, that is the exploitation phase of quantum physics, starts from 1960s to 70. Okay. And this period actually is defined as the first quantum revolution. I'm not saying that GPS was there in the 1960s or 70, but this is just the times, you can say time period when in the quantum physics, this exploitation phase was initiated, right? Then there was a second quantum revolution as well. Okay, now in the second quantum revolution, in which actually the concept of quantum computing was arose. Okay, and this is comprising of these four aspects. That is, the basic science is comprising of these things, that is communication, computation, simulation, and sensing and meteorology. Okay, for example, if you just focus on weather forecasting. Okay, earlier, maybe 20 years back or maybe 50 years back, when the weather forecaster were predicting something. Okay, suppose they were saying that rain will be there in that portion or this portion. The most of the cases, their prediction was inaccurate. But nowadays, when there is a prediction, okay, there are bright chances that whatever they have predicted, it comes good. Okay, so that means there a lot of changes has taken place into the maybe weather forecasting or these type of things. Okay, so basically what we can say is that these things have improved over the time. Okay, with the help of some engineering and some software, some education and training, these type of things were there, which comes under the category of second quantum revolution. Okay, in case of first quantum revolution, first the basic thing was exploitation. Okay, but in case of second revolution, it was exploration. Okay, initially it was just used for the exploitation purpose, but in the second scenario it was for the exploration purpose. Okay, and after the second revolution, it was assumed that quantum technologies were come into picture, and quantum computing is actually one of them. Okay, actually the idea of quantum computing was originated by a scientist named as basically Richard. Uh, basically the idea of this quantum computer was given by Richard Feynman. Okay, and he is also known as maybe a father of quantum computing. You can term that thing as well. Okay, and he was actually one of the first to think of an alternative computer in approximately 1982. Okay, his idea was, as we were discussing, actually Feynman was the first scientist, or you may say the father of the quantum computing. Okay, and his idea was basically of using computer was that instead of for the calculation purpose, we are not going to use classical objects such as bits. Rather, we have to use some other object in which quantum behavior could manifest them visibly. Okay. Now, what we mean by this quantum behavior indicates, as we have discussed, that quantum behavior is such type of behavior in which we are able to actually look the things in real world. Okay. When object-oriented programming was initiated, it was termed as that they are very close to real world. So basically, the major cause of inventing the object-oriented programming was that we wish to look into the real objects. Exactly in case of quantum computing also, we are trying to look every aspect of a particular object. We are trying not to miss even a single object. Okay, so that type of scenario is there with this thing. Okay, this is a quote which is given by Richard Feynman. Okay, and the quote states, "Nature isn't classic, damn it. And if you want to make a simulation of the nature, you would better take it quantum mechanical. And by golly, it is a wonderful problem because it doesn't look so easy." Okay, what it is trying to say that in real life, we don't have classical problems. We are actually having a different type of problem which are quantum in nature. That is all the possible states. There are some states which are unpredictable. Okay, so those states are also to be taken into consideration, and for that purpose we have to use quantum mechanics. Okay. So this was a bit about this. With the sentence reported in the previous slide, the phenomenon attracted the attention of scientific community, and that's why quantum computing was initiated. Okay, when the quantum computing was initiated by Feynman, there were number of other scientists. Okay, one was Deuced, other was Benioff. Okay, so they were also trying to use the concept of quantum computer. Okay, and in combination of those three scientists, quantum computing was originated nearly from 1980s to 1990s. Okay, so that was the era when quantum computing was originally initiated. Okay, then we come to the basic building block of quantum computing, and the basic building block of quantum computing is qubit. Just like in case in our computer till now, the basic building block is bit. Okay, 0 and 1 state. Okay, but in case of this quantum computing, the basic building block is qubit. Okay, in classical computing, the basic logical unit is, we know, as we already know, is bit. Bit is capable of storing only 0 and 1. Okay, and bit is considered to be the basic logical unit. We already know this thing, so I don't think I should go through this. Okay, but in case of quantum computing, the idea behind quantum computing is to replace the bit with something that is capable of manifesting evident quantum behavior. First of all, superposition. That means we wish to identify such type of you can say bit, or such type of basic ingredient or basic building block which is able to show the quantum behavior, and one of the behavior is obviously superposition, which is the most important one. Okay, and for that purpose we are using qubit. Okay, if you look at this, this is basically a sphere which is showing two direction. That is, one is the north direction, other is the south direction. Okay, in the north direction actually 1 is written, in the south direction 0 is written. Actually these 1 and 0 are still the classical bits. Okay, this basically you can say is a structure of the qubit. And there's something that is which is able to behave like quantum, which is able to show the quantum behavior, actually is termed as qubit, right? Now we look upon this qubit in a bit more detail. A qubit is the quantum equivalent of a bit. Okay, it can be represented by an atom. Okay, so this is the representation. Trapped ion or a macroscopic object which under particular condition can exhibit quantum behaviors. Okay, so basically qubit is able to show the quantum behavior depending on the whatever conditions we are applying. Okay, just like this, initially this is the north pole, this is the south pole. These are the two poles which are represented by a qubit. Okay, and maybe this position, this is basically a qubit superposition. Okay, now this qubit is able to show all the possible you can say all the possibilities between 0 and 1. Okay, that is, the final output still will be either 0 or 1. Okay, but you are able to show the superposition positions as well. Okay, in this case it is able to show both 0 and 1. Then the principle of measurement has been applied. Okay, and it is showing two outputs, that is 0 and 1. Still it is showing the two outputs which are again 0 and 1, but in between superposition principles are also applied, right? Next is, on the basis of qubit chosen, it is determined what state is the 0 state and what state is the 1 state. Okay, actually the direction of the current that runs through the superconducting qubit or the spin of the atom, actually 1 or 0 can be identified. That is just an example. It is not necessary that it will be identified by this. That can be one of the things. That is, you can check that what is the direction of current in an ion. Okay, so depending on that it will be either 0 or 1. Okay, so, or you can say, if suppose you are representing it via an atom, okay, in that case the spin of the item, whether it is clockwise or anti-clockwise or whatever it is, depending on that, the state of 0 and 1 will be represented via the qubit. Okay, so in that manner, the qubit actually will allow us to use the quantum effect. And when we are applying anything, when we are creating any circuit, so we will be able to incorporate the quantum behavior in that particular circuit as well. Now the question is, how can we manipulate qubits by taking into account the effects induced by quantum mechanics? Now the next important question is how to manipulate the qubits. Suppose we are having the qubits, how to manipulate them? Okay, so for doing this, we need to start introducing the concept of quantum computing. So now we come from the qubit, we are moving towards quantum computing. So quantum computing is a science that combines the mathematical formalism of quantum mechanics with the creation of computing circuit of classical computation. Just like as you were creating the basic circuits for a PC, you can say. Similarly, with the help of quantum computing, we will try to create circuit using which will be using some operations. We will try to understand the various type of gates and all those things. We will try to understand. Okay. So for fully understanding this, we have to use some tools. So before using those tools, we must know a little bit about linear algebra and quantum mechanics mathematics. Okay, so we'll be focusing on that. Okay, so to understand the basics of quantum computing, it is not necessary to be, we have already done this thing. Okay, so the first term that we use in quantum mechanics is direct notation. Okay. It is all either termed as direct notation or it is termed as bracket notation as well. Actually, bracket is divided into two parts, that is BRA, first part, bra, and second is KET, ket. Okay, so these are the two terms which are used, and we can say those terms as direct notation as well. Okay, in the direct notation, we are using this, that is the psi. This is also termed as ket notation. When this is a straight line, then this is a angular line. So this is termed as ket notation, and this first it is angular line, then it is straight line, then it is termed as bra notation. Okay, so this ket notation is using psi. Okay, in that case, this is psi 0, 1 up to n, and this is rho, and which is representing, actually the symbol is rho, and it is also representing rho. Rho 0, rho 1, and likewise. Okay, so these are the notation for representing the vector, right? Another thing that we'll be using is how to identify the dot product, or you can say that it is identified like this. Okay, so this is basically angular bracket, then row, then straight line, and then this, and the dot product is represented with I vary from 1 to n. And now this representation is complex number. Okay, actually in quantum mechanics we use complex numbers. Why we are using complex numbers? The basic reason behind using complex numbers is that is, in case of normal linear algebra or in case of mathematics, we are only using real numbers. Okay, but it is not the case that only real numbers are available in the space. There are complex number available in the space as well. That's why quantum mechanics also focuses on the complex number, and this product, this is the dot product, which is belonging to a set of complex numbers, right? And then there is another type of product which is defined, which is termed as tensor product or outer product, and this is defined like this. This is the symbol that is used for this. This is the symbol which is used for tensor product. Okay, and it is represented as using curly braces and all those things, and still it is belonging to the complex set n cross n. Now, why it is not written as n cross n over here and why it is written as n cross n, you will see by an example which will be followed by this slide. Now, next is matrix vector multiplication. I hope most of you are familiar with this. If you know a bit of mathematics, so this is nothing but simple two matrices are there, 2 by 2 and 2 by 1, and the resultant is a 2 by 2 matrix. Okay, sorry, resultant is 2 by 1 matrix. Okay, so correspondingly, this matrix vector multiplication is there, nothing much. This is the example for the vector matrix vector multiplication. So again, nothing much. So I don't think I need to discuss this. Now we come to the new type of product which is defined within this quantum mechanics, that is tensor product between matrices. Okay, suppose you wish to multiply these two matrices, but here the operator is tensor product. Okay, in case of tensor product, you have to first consider A11, and then you have to, this will act as a scalar, and this matrix will be there. So this matrix, the final matrix, if it is 2 by 2, if it is 2 by 2, will be comprised of 4 by 4 matrix as the answer. So that means there will be a total number of 16 entries in this matrix if it is tensor product between matrices, right? Then there is another matrix that we use in quantum mechanics, which is termed as unitary matrix. Okay, now what is a unitary matrix? Unitary matrix is basically, you can say, is the conjugate transpose of a square matrix. Suppose we are having a complex square matrix U, okay, then U star is conjugate transpose of that matrix. Now what we mean by conjugate transpose, let me explain you. First, you have to take basically the transpose of input matrix. Whatever is your input matrix, you will take transpose of that. Okay, and after that you will calculate the conjugate. Conjugate means if there is an imaginary number. Suppose, what is the imaginary number? Imaginary number is nothing but iota. Okay, we generally denote imaginary number by iota in mathematics, right? So if you are representing it via an iota, so if there is a positive symbol with iota, you will put a negative symbol. If there is a negative symbol with iota, you will put a positive symbol. That is basically the conjugate transpose. Okay, so basically you have to take transpose, then you have to calculate the conjugate. So that becomes basically the conjugate transpose, or you can say the unitary matrix. When it will be termed as unitary matrix, it will be termed as unitary matrix when you multiply the matrix with its conjugate transpose or vice versa, then the resultant should be an identity matrix. If it is coming to be identity matrix, then it is a unitary matrix, otherwise it is not. Just look at this. This is just an example of a unitary matrix. For example, if we say this is a matrix, okay, and we multiply this, the resultant is this. So in that case, if this belongs to a complex number, then TZ should also be equivalent to this complex number matrix, right? There is another term that is used in case of quantum mechanics, that is Bloch sphere. Okay, actually this is a sphere which is termed as Bloch sphere. Okay, a qubit is defined as a ray of the Bloch sphere. Okay, so basically if you put a ray in between, okay, so this will be defined as a qubit. Starting from this point to this point, this is a ray. This point to this point, this is again a ray, this is a ray. Okay, so all the rays from this are termed as a qubit. Okay, the Bloch sphere is a mathematical object defined in C square. C square, what is C square? C square is complex number set, that is C multiplied by C, you can say that particular thing, whose elements on the surface can be identified by the coordinates. Okay, now the coordinates are identified like this, that is cos theta by 2. Okay, theta is the angle that is identified via this. Okay, so this is the 0 value, this is the north pole, this is your south pole. Okay, and in correspondence to this, you will be identifying this theta angle. Okay, so whatever is the angle, so correspondingly you will be identifying cos theta by 2, and then e raised to power this I indicate iota over here, and then this is I, and sine theta by 2. Okay, so this is the, you can say, mathematical object defined. This is the Bloch sphere which is defined mathematically. Okay, the poles of the Bloch sphere represent the classical state 0 and 1 as it is represented. As we can see, they are highlighted in direct notation and are defined by these two vectors. Okay, we can analyze the Bloch sphere only in the real world, ignoring the variable phi and bringing us back to the circumference. Okay, so that means this phi actually can be ignored. Okay, and we can actually only involve the real things instead of involving the complex things. Okay, so this can be represented like this. This psi can be represented like this, that is alpha, beta. Alpha and beta are two, you can say, possible values. Okay, for example, in case of bits, there were two possible values, 0 and 1. Okay, here the values are alpha and beta. Okay, so alpha may be 0, beta may be 1. You can consider this thing, or it may be the case that the output, that wherever your point is there, okay, wherever your data is available, the data might be in between somewhere. Okay, so this is represented like this, that is cos theta by 2 sin theta by 2. Look at this. In this case, we have ignored the imaginary value. We have used only the real values. Here 0 is represented when the value of theta is 0. So it is 0 when it is 180. This is the 180 angle. So correspondingly it is 180. So correspondingly the value is 0, 1, and here it is 1 and 0. Okay. If there is any in between value, suppose it is neither pi nor 0. Okay. In that case, with this choice of, you have identified the classical states. Okay. So these classical states are as it is, as we were considering in a normal PC. Okay. Any other state of the system can therefore be represented as a linear combination of the classical states. Just look at this. This is your original matrix. Okay. Now this is represented with the help of linear combination of the classical states. Classical states are only two, that is 0 and 1. Okay. So you have represented in between value, suppose at this point or this point, depending on whatever angle is there, whatever is the value of theta. So corresponding to that, you will be trying to identifying the value of alpha and beta. So the answer will be alpha multiplied by 1, 0, and like this. So correspondingly, alpha will be multiplied by this first classical state, and beta dot product of beta multiplied by the second classical state. Okay. So this particular intermixing, or you can say the linear combination, is termed as basically the superposition. Okay. Written in this way, the relationship between the coordinates of the qubit and superposition principle begins to appear clear. Okay. So that is a bit about how the superposition principles are represented in the classical, in the quantum mechanics, or you can say quantum computing. Okay. Now, after identifying the superposition principle, the next thing is another term that we use in case of Bloch function is wave function. Okay, that is again an important aspect. One was the superposition. When we were discussing the principle of quantum mechanics, the first principle was actually this superposition, and the second part of the first principle was measuring a qubit. Okay, here the measurement of the qubit is done via a special function which is termed as wave function. Okay, now how the wave function is calculated, even if it can be represented, will never be possible to observe a state of superposition. Okay, that is just about superposition. Quantum computing, like classical, involves the measurement operation which aims to make know the value of a certain qubit or bit. Okay, the thing is, the purpose of measuring a qubit is that what will be the value of this bit, whether it will be 1 or whether it will be 0 or whether it will be something different. Okay, so that is what we know as measuring a qubit. For that purpose, we use a wave function. Okay, so the fundamental difference is that the measurement of a qubit destroys the superposition state. Whenever you try to measure a particular qubit, the output will be either 0 or 1. Output cannot be in between state. Okay, and now if the output is either 0 or 1, that means the in between states, the superposition states, you are removing and you are forcing them to be converted into either of the classical states, that is either 0 or 1. Okay, so that is termed as basically the collapse of superposition, or you can say the collapse of the wave function. Okay, here we are using two variables, that is alpha and beta. Now what are these alpha and beta? These alpha and beta are commonly termed as amplitudes and are directly related to the probability of observing qubits in one of the corresponding classical states. Okay, so basically these are telling what will be the probability of getting into the classical state 0, or what will be the probability of getting into the classical states 1. Okay, so these are termed as amplitudes of that thing. Okay, now the probability, how this probability is identified, the probability, this symbol is used for probability. Okay, so this is identified like this, that is the cat psi is equal to 0. The probability of this being 0 is alpha square, and probability of this being 1, that is the qubit being 1, is beta square. Okay, so this is how it is represented for these states. And important thing is, the sum of this alpha square and beta square should be 1. Okay, just like you say the sum of all probability should be 1, exactly same principle is followed over here, that is alpha square and beta square should be 1 over here. Okay, so corresponding to that we can define like this, because alpha we were stating as cos theta by 2, so we'll be saying alpha square is cos square theta by 2, and similarly we will be stating beta square as sine square theta by 2, and that should be equal to 1 for all theta. Okay, so that is how you can define this Bloch sphere. Okay. Further, if you look upon this, suppose you wish to define this psi. Okay, instead of 0 and 1, you are taking an in-between position. The angle is 90 degree. Okay, so correspondingly, it will be treated as theta by 2. Theta is pi by 2, so it will become pi by 4. So the correspondingly answer will be, root 2 divided by 2. You know the value of pi by 4. So correspondingly, this will be the answer, or this can be represented via 2 qubits in this manner, that is square root of 2 into 2 multiplied by alpha, which is 0. This multiplied by beta, which is 1. So correspondingly, this value is identified. So the probability of this being 0 is equal to probability of this being 0, and the probability is 50% that this data can lie either, this data can either be 0, can either be classified into 0, or it can be classified into 1. Okay, so the probability in both the cases is 1. Now we are checking another criteria, that is, suppose this is the point on this line, we need to identify what will be the probability of this. Okay, so in here the theta is 3 pi by 2, so correspondingly the answer is coming out to be only the negative sign. This is the difference, otherwise the things are same. Okay, so again the probability is same, 50%, that alpha being this and beta being this is the probability, which is 50%. Okay, now we are taking one more consideration, but now the consideration is taken into picture. Here we are having 2 qubit system. Earlier we were having only a single qubit system. There were only a single qubit, but now we are considering another system which is having 2 qubits. Okay. Now here, because there are 2 qubits, one qubit is termed as psi 1, other qubit is termed as psi 2. Okay. Here the angle is assumed to be 60. Here the angle is assumed to be 120. Okay. Now the question is, what are the mathematical representation of these 2 qubits as a function of the classical states? Okay. So let us look upon this. For the first scenario, corresponding to angle 60, this is the representation. Corresponding to angle 120, this is the representation. Okay, so you have identified the superposition. Now the question is, what is the probability of both? Okay, now for identifying the probability, we will be finding this, the probability of being 0 of this particular thing. Okay, first we are identifying the probability. Now look at this, this is 1 by 2, this is square root of 3 by 2. Square root of 3 is I think 1.7, something like that. Okay, so obviously this value is greater, this value is smaller. Okay, when you try to identify the equivalent percentage, you will be able to identify this, that in this case this value is higher, this value is lower. Correspondingly the probability is 75% and 25%. Okay, and in this case similarly this probability is coming out to be 25%, and this value is coming out to be 75%. Question is how we have identified this thing. What we have done, we will be finding alpha square, we will be finding beta square, so that it becomes 1, and correspondingly this 75% and 25% have come exactly in the same scenario. This is your alpha, this is your beta, alpha square, beta square. Correspondingly this probability is identified. Okay. So this is the picture that comes for 60 and 120. Okay, so overall what we can say is, this is the table for overall table, that is, if we are considering 2 qubits at the same time, then the probability of both being 0, that is, this is 0 and this is 0, that comes to be 18.75%. Now how we have calculated, we have just calculated the 100% of all these things, and correspondingly we have divided it. Okay, so correspondingly it is coming out to be 0, 0. The probability of this is 75%, the probability of this is 25%. If you evaluate this, this comes out to be 18.75%. Okay. Similarly, the probability of first being 0 and second being 1, first being 0 and second being 1, this is 75% and 75%. Correspondingly, the overall probability is coming out to be 56.25. And similarly, this is 25, 25, correspondingly very less probability. So in that manner, you are able to identify the probability of the two classical states. Okay. That is, meaning is that if both are coming 0, this is the probability 0, 1, likewise. So these are the various probability if you are considering a 2-qubit system, right? So that is a bit about this. I think that we have completed. Okay. Now, if we further go into this, now by extracting the square root of the values obtained in the probability, we can obtain the description of the wave function relative to the system composed of the 2 qubits. Okay, so correspondingly, with the help of probability, you are able to identify that whether it will fall under 0 category. For example, if it is 0 and 1, then because the probability is 50, so it will fall under 1 category. Okay, so corresponding to the probability, you will be able to identify whether it will fall in one category or whether it will fall in other category. Now, overall, the wave function is indicated like this. Like this is the 0.43 multiplied by this and all this. So the if the input is this, okay, so if the input, you can say the qubit is saying 0, 0, then what will be the output? So that depends actually on the operations that you are applying. After considering the qubit system, this is just the representation, that is both are 0, this is the probability, and correspondingly this value will be multiplied 0, 1, correspondingly this value. This has been calculated via these values actually. Okay, so you get the total of this and you divide it by 4, correspondingly you will be able to identify these values, right? So this is, you can say, another representation of 2-qubit system, how those probabilities are calculated. Okay, now in general, that was a specific example. Now this is the generalized example of the 2-qubit system. Okay, if suppose psi1 is represented like this, alpha 1 is some value, correspondingly beta 1, and correspondingly alpha 2, beta 2. How to calculate the probability? Just find the square of this and square of this, and correspondingly square of this, and 0, 0 is just calculated by multiplying this alpha 1 square with alpha 2 square, and correspondingly 0, 1 will be calculated as alpha 1 square into beta 2 square, and similarly this table will be generated. Actually, these probabilities have been calculated via this value, and this 0.43, 0.75 has been calculated via these values, that is psi1 psi2 is equal to alpha 1 multiplied by alpha 2 and then 0, 0, and corresponding to this, these values have been calculated. Okay, so that is how you can calculate the basically superposition principle, or you can say how to represent the 2-qubit systems. Now this was for the 2-qubit system. Similarly, you are able to represent the data using 3-bit system. In case of 3-bit system, you have to consider all possible combination. In this case, only 4 combination were there, 2 raised to power 2. In this case, there will be 8 combination. Okay, all alpha, beta, alpha, alpha, beta, likewise. Okay, so all the combination has not been shown over here. Ellipsis has been shown. So these combination will be there. So if it is n, so there will be 2 raised to power n combination. So many combination will be there. So the major advantage of using this quantum computing is that we can use not only a single qubit system, we can use 2-qubit system, 3-qubit system, or even the multi-qubit system as well. Okay, so that can be used in case of quantum computing, right? Okay, so in general, a system with n qubits is completely described by a vector of 2 raised to power n, as I told you anyway. Okay. So actually, you can represent this via this representation as well. This is basically the symbol used for tensor product. That is, this can be represented as psi1, then tensor product of psi2 and tensor product psi-n, or in other words, you can represent like this, that is psi1, psi2. Okay, it is assumed because when there is a tensor product, it will be cat and bra. Okay, so if that is the scenario, so that will be assumed as a tensor product. Okay, so that is how you are able to identify the able to represent this multi-qubit system. So that is the scenario. Okay, another important thing is you can represent this system using this representation as well. Okay, eta can also be used for this representation, that is eta 1, then 0, 0, 0, eta 2, and likewise. Okay, but the important thing is that it is not reversible. Okay, meaning is that you are able to represent this using eta. Okay, but vice versa, it may be possible, it may not be possible. Okay, the reverse is not 100% true. So in general, we will say that reverse may not be true. Okay, so that you have to remember in case of multi-qubit system. So till now, we have discussed the basics of, you can say, quantum computing. So till now, if there is any queries, we can discuss. Okay, so I think we may continue. This I think program is not required. This is just the gate representation of some circuit. Okay, yeah. Okay, there is a question. Question is there any way so that we are able to represent how many qubit system is required? Actually, that depend on the complexity of the problem. For example, when we are solving some algorithm, when we are writing an algorithm, okay, if we are able to write a classical algorithm for a particular, if we are trying to write a classical algorithm for a particular problem, in that case, single qubit might be enough. Okay, because we are using we are using bit system in that case, so single qubit will be sufficient. But whenever we are using, I hope you are familiar with the NP hard problems. There are some problems which are termed as NP hard, that is non-polynomial problem. Okay, so when we are dealing with non-polynomial problems, in that case, multi-qubit system is used, but that actually depends on the problem. We cannot guarantee that it will be fixed with 3 qubit or 4 qubit. So we cannot state in general. It depends on the problem. Problem to problem, the number of qubits may vary. Okay, so that is the answer for this, I think. Okay, thank you. So now we come to the manipulation of the qubits. Okay, so when we talk about classical system, in that case, we are using 3 type of gates, that is AND, OR, NOT. Okay, along with that, we are using XOR gate. Along with that, we are using NAND gate. Then we are using NOR gates. Okay, and we already know that there are 3 basic gates, that is AND, OR, NOT. Okay, and then there are universal gates, that is NAND and NOR. Okay, then there are some additional gates like XOR and XNOR. These type of gates are available. Okay, and another important thing is that from input you are trying to produce the output, vice versa is not true. That is, they are not reversible. Okay, so whatever is input, corresponding to that some output is there, but if output is present, you are not able to get the input. So reversible scenario is not there with the classical system. Okay, but when we shift our attention to quantum gates, okay, so the thing is, we will now be focusing our attention on the quantum gates. Okay, so when we are using quantum gates will be represented in terms of matrices. Okay, not necessarily always they will be represented in terms of matrices, but whenever we will be performing some operation, the operation will be represented in terms of vectors and matrices. Okay, although the representation of the gates will be comprising of some lines and name of the, you can say, gate. These type of things will be there, but basically the operation will be in terms of matrices. Okay, so that will be represented like this, either this matrix or this matrix or 2 raised to power n matrix. So these type of matrix will be used in case of quantum gates. Okay, so that is the prerequisite. Okay, important thing is that these matrices, they must be unitary matrices. I hope I have already told you what we mean by unitary matrix. That is whose conjugate transpose, when you calculate the conjugate transpose and when you multiply by that, that is coming as identity matrix. That is a unitary matrix. Okay, and the second aspect of that is that the number of input qubits must be equal to number of output qubits. Now, this is the difference in case of classical mechanics and quantum mechanics. In case of classical computers, it was not necessary that the number of inputs were equal to number of outputs, but in case of this thing, we are saying the number of input qubits must equal to the number of output qubits. If the number of input qubits are 1, output qubits will also be 1. If the number of inputs are 2, qubits are 2, the output will also be 2. Okay, so as you are asking a question that how many bits to decide, so that will depend actually how many outputs are required. If you are requiring only a single output, in that case single qubit will be used. If you are requiring multiple outputs, in that case multiple qubits will be required. So that type of scenario is there. Okay, another thing is it is possible to make these operation reversible. That is, in case of quantum mechanics, we are able to produce the reversible circuits. Just look at this. This is the irreversible, or you can say the classical type of thing. Here, it is a reversible circuit. We are having 2 outputs, although we might use one output or we may use both the outputs, depends. Okay, we have added here, we have just shown a garbage output, or you can say dummy output. Whatever is the input, that is exactly the output. We are actually implementing this, but this needs to be presented in case of quantum circuits, quantum mechanics. Now, these are some of the gates which comes under the category of quantum gates. The first gate is NOT gate. Okay, NOT gate, the basic purpose is that it will convert 0 into 1 and 1 into 0 as a simple NOT gate does. So it does exactly same. Here, the input is represented in terms of qubit. So qubit is 1 and 0. Okay, so this is your matrix. Okay, this is a unitary matrix. Okay, so corresponding to that, this was the input qubit and the output is 0, 1. So if this was representing 0, then this will represent 1. Okay, if this was representing 1, this will represent 0. So correspondingly, the output will be there. That is, if this is the input, 0 is the output, then the output will be in the reverse order. That is this thing. So this input is assumed as 0. So this will flip it into 1 output. Okay, so that is the NOT, very simple gate. Similarly, another thing is this was just for 0 or 1. Okay, if the value is neither 0 nor 1, it is a superposition. So if it is a superposition, in that case, it will be obviously alpha beta. It will switch the values. That is, alpha will be converted into beta and beta will be converted into alpha. So the final output will be, that is this alpha. When you multiply this will come out to be beta plus alpha. So correspondingly, this will be alpha into 0 plus beta into 1. That will be flipped. Alpha will be flipped with beta and beta will be flipped with alpha. Okay, so that is just whatever is the input, it will convert, reverse that. That it will change the state of the input. You can say this thing. So this is single qubit quantum gate, that is X gate. What it is doing, this is the input. So output is reversed. Alpha is converted into beta, beta is converted into, okay. So in this case, the bit flip will take place. This is basically state change. Then Hadamard gate, next gate is Hadamard gate. Okay, now what does this gate does? Okay, actually it does not, you can say, reverse the input. Rather, if you focus on this, it basically changes the phase of the input. Okay, so if this was the input, this is the 0. Okay, now it has converted its phase. It is not changing the state, rather it is changing the phase. Okay, so this was the input. Okay, the output is coming out to be this thing. Actually, I think I can explain it via some examples, but now I'm sticking to this. I will come to a website in which I will be showing you that how you can be familiar with gates with a lot of examples. I will be showing you, but after completing that, this. Okay. So in this case, 0 is converted into this thing, that is 1 by 2, and then corresponding to that 0 and this thing. So this is the change of the state in case of Hadamard matrix. Okay, I think I must show that. Give me a minute. Let me share a different thing. Give me a minute. I hope a different tab is visible to you. Is it visible? Is it visible? If you can tell me, please. Okay, thank you, Vinit. Okay. So let me show. Actually, this is a website which is termed as Quantum ML Handbook. Okay, and this is from GitHub. Okay, I'm using it using GitHub. Okay, so let me show it to you. Let me explain the gates from this place. I think it will be better over here. Give me a minute. Okay. Fine. So let me explain over there. So basically, there are 3 types of gates that we generally discuss in case of quantum computing. One is termed as single qubit gates that we were considering. Other is multi-qubit gates, and other is universal gates. Okay. And under the single qubit gates that we were considering, there are poly gates, Hadamard gates, phase gate, T gate, S gate, and U gate. And under the multi-qubit gates, we come under the category of C0 gate, then Toffoli gate, swap gate, and under the universal gate, the similar type of gate that we have already discussed, that is Hadamard gate, T gate, and C0 gate. Okay. Now let us first discuss this poly gate. Okay. Poly gate, under the poly gate, there are 3 more gates, that is poly X gate, poly Y gate, and poly Z gate. Now, why these 3 gates? Because we have looked upon the sphere, that is quantum computing is based on that sphere that we were showing every time. Okay, so in that case, there are 3 dimensions, X, Y, Z, and corresponding to those 3 dimensions, these 3 gates are there. Okay, now what are the effect of these gates on the qubit? Okay, why they are termed as poly gates? First thing is that it was and the purpose of the poly gates are 3 purposes are there. One is the bit flip operation, other is phase flip operation, and other is bit phase flip operation. Okay, now when we are using poly X gate, actually we were using poly X gate initially. When we defined in the PPT, we were defining the X gate or NOT gate. Actually, NOT gate or X gate is also termed as poly X gate. Okay, so poly X gate is basically changing the state of a qubit from 0 to 1. That is the purpose of bit flip. That is termed as bit flip, and that is termed as poly X gate. Okay, and when qubit is when the phase of the qubit is changing from +1 to -1 or vice versa, we will see via some examples, that is termed as poly Z gate. Okay, so the poly Z gate is that type of Z gate in which we will be changing the phase of the qubit from +1 to -1. We will look at via some example. Okay, and the third type of scenario is bit flip operation, bit phase flip operation, in which we are able to perform both the things. That is poly Y gate, it is termed as poly Y gate, which is changing the state of the qubit from 0 to 1 and vice versa, and also changes the phase of the qubit from -1 to +1 and vice versa. Right, now look at this. As I told you, that poly X gate is also termed as NOT gate. Poly Y gate is termed as bit phase flip operation. That is, it is inverting or reverting the bit, not just like NOT, and it is also converting the phase, and Z gate is just for the phase. Okay, now the metrics that are used in case of poly gates are, for poly X gate, this is the matrix that is used, 0 1 1 0. Poly Y gate, this is a complex number, that is minus iota, then 0. Okay. And in case of poly jet gate, it is using 1 0 0 minus 1. Okay. And the representation of these poly gates are, these circuitry representation is X is represented like this, Y is represented like this, and Z is represented like this. And just look at the example. In the example, let us assume our input qubit is 0. Okay, this is the input qubit. Okay, and when you apply the poly gate can be written as this sigma x. Okay, sigma x 0. That means you have applied the poly gate operation. The answer will be 1. And this will be represented like this. Initial state is this, and you have applied a NOT, correspondingly output is there. Similarly, if you apply a poly Y gate, okay, poly Y gate is applied to this matrix. Okay, look at this. This is minus iota and iota. Okay, and the Y gate is changing just the state. Okay, so if you focus on this, if your input is iota, look at this, we are applying this on iota. Okay, so in this case, so after applying that transition of the input was 0. Now it is transited, or the state of this has been changed to iota 1. Okay, so that is the representation of the poly Y gate. Similarly, if there is a poly Z gate, okay, in that case there will be the combination of two things. That is, in this case, if this is the input, I'm sorry, in this case, Y circuit was combination of two things. One was the change of the state, other was the other was the phase change as well. Okay, in this case the input was 0, input has been converted into 1. Okay, and it was a real number, now it has been converted into imaginary number by multiplying with I. Phase has also been changed. In case of poly Z gates, in this case the input was this plus 1. Okay, now phase has been changed by changing the symbol of 1 with plus to minus 1. Okay, just look at this, applying the qubit, flipping the phase of plus 1 component while leaving the 0 component as it is. Okay, so that is the purpose of Z state. Okay, so just look at this, plus has been converted into minus. So that is what we mean by poly gates. Okay, and poly gates, these are some of the properties. Properties are, number 1, the poly gates are Hermitian. Hermitian meaning is that the conjugate transpose, that is why exactly the same unitary matrix is there. And other is poly gates are involutory. That is, if you apply the gate twice, that is, if you multiply the gate with each other, if you multiply the matrix with each other, you will get the identity gate. Okay, the poly gates are unitary gates, exactly the same thing that we have explained. So these are the examples. So these are the inverse. So these are the aspect of poly gate. Okay, followed by, as we were discussing actually this gate, Hadamard gate. Okay, now what is a Hadamard gate? Number 1, it was given by this scientist, that is termed as Jacques Hadamard. Okay, and the purpose of Hadamard gate is, it is used to change the state of the qubit in terms of X and Z axis of the Bloch surface. That is, it is not working on the Y surface, it is just working on two surfaces or two axes, that is X and Z axis of the Bloch surface. Okay, and the purpose of Hadamard gate is to perform the bit flip and phase flip operation. In the poly gates, there were 3 possible scenarios that you were able to perform bit flip with the x-axis, you were able to perform the phase flip, and you are able to perform both the operation. But in this case, only 2 operations are possible, that is bit flip and phase flip. And this circuit actually behaves similar to poly gates, except the combination of these two is not available. Okay, so because it is changing the state from this to this and vice versa, that is the purpose of qubit, that if the qubit is 0, it will change it to this. And second one was that it is changing the phase is changed from +1 to -1. Okay, so that is the thing about this. When the qubit is in state 0, it means it is this state with the probability. This is the thing. Give me a minute. Okay, so what it is saying, when a qubit is in state 0, so it is guaranteed to be in 0 with probability this, and it in state 1, but Hadamard gate transform this 0 state into an equal superimposition of 0 and 1. What it is doing, again, I think I can now show you the presentation. I can go back to the presentation. Let me give me a minute, please. I need to share the presentation again. Okay. So what we were saying in that thing, we were saying in the previous polygates, we were shifting our attention from 0 to 1 state. But in case of Hadamard, we are converting the 0 state into an in-between state, that is superposition state. This state is neither 0 nor 1. So exactly 50% probability of being 0 and 50% probability of being 1. So exactly that has been done by the Hadamard gate. Okay, so what Hadamard gate is doing, it is converting your input into a superposition type of output, that is 50% probability of being 0 and 50% probability of being 1. Okay, so that is bit about Hadamard gate. Okay, so I hope you have understood the Hadamard gate. So if there is any issue up to this point, we may discuss. If there is any doubts up to this point, we may discuss. Otherwise, time is quite less. I can show you from this only. Okay, I think it will be better to show via this because it is in short. Okay, so this was bit about Hadamard gate. Similarly, there is another type of gate which is termed as phase gate. Okay, and as the name is indicating, it is used for converting the phase only. That is, it is not converting the qubit. It is converting only the phase of +1 to -1. Okay, so this is the gate, and whatever is the input, if input is 0, okay, 0 will remain as it is. There won't be any change in the 0. But if there is an input, for example, in terms of maybe 0 plus iota 1, okay, so iota will be converted to minus iota likewise. Okay, so that is bit about phase gate. Similarly, there is another type of gate which is termed as T gate. Okay, T gate is again used to change the phase, but the phase is changed just by 45 degree. Okay, so that is bit about T gate. Okay, so that was bit about some fundamentals with reference to this quantum computing. So if there is any query with reference to this lecture, you may ask. Otherwise, I think I need to stop right here. So if there is any query, please ask. Vinith, tunneling effect right now, it is not possible to happen, but maybe in future it might happen. Right now, we can't say tunneling. Okay, there was one more question. I think I have missed that. Let me check.
Sir, another question is how these gates are used with real world data or features?
Actually, these gates are used with the help of, actually, as we have shown in these all the gates, there are some matrices. Okay, so the qubit will be represented again in terms of a vector. Okay, so correspondingly, these gates are designed so that they are able to handle these matrices. Okay, so likewise. I hope it is all right.
Any other query? Participants? If you have any question, please use the chat feature.
Okay, there is a question that is entanglement is possible between only two objects. No, that is not the case. Entanglement is also possible between multiple objects as well. It is also possible. It might happen that maybe there are three objects and maybe two are known to us, and on the basis of that third object we can predict, or vice versa could be there. That is, if maybe one input is there, on the basis of that next two output can be predicted. So it is possible to have entanglement on more than one objects as well. More than 2 objects, I'm sorry.
Participants, any other question? Now, thank you everyone for your active participation and engagement in session 1. A big thank you to Dr. Pradeep Kumar sir for his insightful presentation on quantum computing and machine learning fundamentals. It was a fantastic start to our FDP. Thank you so much, sir.
Thank you, sir. Thank you. Thanks a lot. Okay. Thank you.
Thank you, sir. Thank you so much.
Thank you. I think I may start my video, although video will be rotated, but still I can start.
Yes, sir.
Sorry about that.
Nice to meet you, sir. Thank you.
Thank you. Thank you. Same here. Okay. Thank you. Thank you, all the participants. It was a wonderful experience to present this presentation before you. So thank you. Thank you, everyone.
Okay, sir.
Okay.
Now let's take a short one or 2 minutes break to recharge and get ready for the next session. Please ensure you're back in time as session 2 promises to be equally exciting and enlightening. In session 2, we will delve deeper into the convergence of quantum computing and AI with our esteemed speaker, Mr. Ashish Tyagi from TCS. Participants, please fill the feedback form as early as possible. The feedback form link is shared in chat as well as in the WhatsApp group. Please make sure to access the link and submit your responses promptly after every session. Participants, your feedback is crucial for us and it is mandatory to receive the certificate of participation. So please don't forget to fill out the form. Thank you for your cooperation. Participants, attendance will be taken from the WebEx platform only. So all of you are required to attend both sessions.
Is Ashish here?
Okay. So welcome back everyone. We hope you had a refreshing break and are ready for our next session. It's time to dive into another fascinating aspect of our faculty development program on quantum machine learning, bridging the gap between quantum computing and AI. Our second session is titled Convergence of Quantum Computing and AI, an area that highlights how these two transformative technologies intersect to create innovative solutions and reshape industries. This session promises to provide deeper insights into how quantum computing amplifies the potential of artificial intelligence. To guide us through this interesting topic, we are honored to have Mr. Ashish Tyagi, is a domain and strategy consultant within the travel, transportation and hospitality unit in TCS. He has over 19 plus year experience in business and domain. He is leading the Logistic Strategic Initiative Group primarily focused on disruptions, innovations, growth and transformation opportunities using digital interventions in the entire transportation value chain. He works closely with industry partners and research teams to take the innovation to a new level. He is a graduate in chemical engineering and technology from IIT BSU, Varanasi, and carries extensive knowledge in industry and processes. He holds industry relevant certifications and has also written the white paper on marketplace offerings. So without further delay, let us welcome Mr. Ashish Tyagi sir to take over and enlighten us with the insights on this cutting edge topic. Over to you, Mr. Tyagi sir.
Am I audible?
Yes, sir.
Yes, sir. You are audible, sir. Good evening, sir.
Good evening. Very good evening to everyone. the respected faculties, the entire audience. It's been a pleasure, and I'm quite delighted to be on for this session. And the way we would like to have this session is I'll just walk you through the agenda, and uh, like in the presentation we would like to we would be going through an introduction to quantum computing. I think much of it has already been covered earlier by Pradeep sir, so I'll try to avoid the redundancies or the repetitions. The second one is about quantum computing in AI, uh, right? And the third one is application of quantum computing in AI. Fourth one is we'll talk about some challenges and limitations, and then the road ahead uh, for quantum computing, right? I hope that my screen is visible, right?
Sir.
Okay. So is that good? I think at the end we can take up some questions. Yeah. I'll try to cover up as much as possible in the allotted time. Uh, so we'll just move on to our first part of the agenda, which is introduction to quantum computing. And here we'll talk about what quantum computing is all about, right? As I said, much of it has already been covered, so I'm seeing an overlap. But we see that quantum computing is an emerging technology that is promising to revolutionize the way we are going to process the information in the future, right? And needless to go back, but just making a mention of what is the basis of quantum computing is all about quantum mechanics. I think most of us have already gone through that, or we understand that how what Mr. Planck, Mr. Heisenberg, right, Mr. Rutherford have already been spoken about, and that is where this idea has been taken from, and this entire concept of quantum computing has been evolving. So I'll not delve into that, but it's something to make a mention that what quantum computing is somehow related to mechanics. It is something which is related to physics, mathematics, an amalgamation of computer science, physics, and mathematics to solve those complex problems at the ease of time, right? And if we look at the value chain of quantum computing, so it starts with the component providers, which are typically the semiconductors or the electrical companies. There are hardware providers, there are software providers, there are cloud service providing companies, there are end users, there are consulting service provide companies. So there's an end-to-end value chain that is involved here. It is just that we need to see which part of the value chain we fall into, right? But it's a entire ecosystem that is evolving at the current stage. uh, then when we talk about quantum computing, let's also make a mention of that quantum computing is all about the way the basic fundamentals it works upon, right? It works upon uh, the data processing unit, which is called as qubit, much very much different from how classical computers or classical computing operate as 0 or 1, right? This gives the quantum computing to solve those problems which were impossible before, right? Because now you have that speed, that dexterity, that ability to solve those complex problems. You had the data, AI was helping you, but still you needed more power, more speed, right, to get to that level. So that is what I think quantum computing is all about. As Pradeep sir has mentioned, see, before I get into that, but what are qubits? Those are basically represented by quantum particles. It could be electrons, protons, it could be atom science or superconducting junctions that are usually given the charge or polarization and they change their state. So I'm just sharing an anomaly how it works at the base level. Now, if we look at what Pradeep sir has already spoken about, the change of state of a qubit, which is the base data processing unit in a quantum computing. Unlike classical computing, quantum bits or qubits, they are able to change their states invariably between 0 and 1. That is that that is just like saying that they can accept any value between 0 and 1, and they follow if you look at this blob sphere on the right hand side, it can represent any point on the sphere. So if you look at a football, for an example, it can be in any place on the football or a sphere where this probability would lie upon. Output or the possibility or the probability of having an outcome would fall into. It's not just that 0 or 1, it could be 0 and 1 all both at the same time. So if I try to take an example, if you look at 0, if you look at a qubit uh, or a 2 qubits, then the number of possible permutation combinations that you can have is 4, right? The processing power. But if I make it to 500 or 2000 or 7000 qubits, that's what today's uh, organizations are offering. Even IBM is offering, or Dwave is offering, is 7000 qubit processing systems, right? Then you could look at the computation power of that those qubits. It is 2 to the power of 7000, right, bits at that point of time. So that is something very implausible, that, right, you can't even imagine what is the processing speed. It's just like you are sitting in a library and you want to read all the novels at the same time, and you are able to do it, right? That is the power of quantum computing, what we are talking about here. I think this classical equation has already been covered earlier, and even the multiple states and the matrix of quantum computing, how it is represented. I'll not just walk through it, I'll just move on to the next slide, which is superposition and entanglement, which is the actual force, the power, or the pillar behind the power of quantum computing, right? So, what is superposition? As I said earlier, it is something that allows an object to take or exist in multiple states at once, right? Or an object or a system, it could be a proton or it could be anything, right? What we are talking about in supercomputing or quantum computing. It can take 0 and 1 simultaneously, and it allows parallel calculations. So that is the excitement, that is the most significant part of superposition that we are talking about. The way we can look at superposition is, we can look at a coin or spinning a coin. So you can assume any values until it falls and until it lands, right? So that is what is superposition all about. That means quantum computers can pass through several possibilities simultaneously, rather than trying each one of them individually, right? So it's a different permutation and combination of values at the same time. Entanglement, as I said, is another characteristic of quantum computing. That means a qubit that has been entangled in another qubit can affect the state of the other qubit, no matter how far they are, right? That means it could be a qubit maybe some kilometers away or many farther distance away, but it's like not just passing the information, it's uh, uh, changing the state of information, right? So that is what entanglement is all about, right? And the most significant use of entanglement and superposition together is in quantum teleportation. A significant attempt was done by Anthony Zillinger in 1997, when he attempted to, when he succeeded in, teleporting the quantum state, the state of certain, let's say, object over a few distance, right? That is where it succeeded earlier, but recently there have been efforts, but due to some other challenges, such as the noise, uh, the noise that creeps in, right? The interference that could lead into errors during teleportation or the entanglement, or it could be related to cyber security, or it could be related to manipulating the information in between. So that need to be addressed. But there are significant steps or efforts that are being taken in the direction of teleportation, right? Uh, I'll just move on to the next slide. Quantum gates I'll not cover. I think these have already been spoken about. Quantum versus classical computing. This is something we need to, or we should be knowing about. So before we get to this, let us try to understand what is the theory of computing, right? As we all know, our classical computers are going through, or the way they understand today is through the bits. It works like a light switch, right? You turn it on, you turn it off, right? And Similarly, they work with the transistors, and they just give you a value of 0 or a 1, where A is the probability, let's say A is the probability of being 0, B is the probability of being 1, and their state can be either 0 or 1, and A and B can lie between 0 and 1 together. The other part of classical bit is like they have low error rates, right? They are quite steady in their prediction, in their output, or in the output that they are going to generate, right? And they can operate at room temperature, and they can solve typically everyday problems, right? But when we look at quantum bit, they usually work with qubits, which we have already spoken about, and their state can be 0 and 1, or it can be invariably any other state at the same time. Uh, I think all these equations have already been explained earlier, right? It just follows the law of circularity, right? A square plus b mod of a square plus mod of b square equal to 1, right? I think that has already been explained in the earlier session. But what is typically important is there are typically high error rates with respect to quantum bits as of now because of the noise and interference that creeps in uh, during their processing, right? And because of this, it needs to be ultra cooled. So if you look at the infrastructure that has been developed, or the typical hardware giants like IBM, they are working upon. They are working upon super cooled or ultra cooled environments, right, for quantum computing to work. Right, that is where even a small variation in temperature can lead to uh, invariably, you know, uh, unexplainable results, right? You can't imagine where it would go, right? Unlike classical bit. So I think that is the drawback right now, but I think the industry is right now working on it, and these are typically used for optimization, data analysis, and simulation, solving simulation problems, right? Not usually in every day because of their scalability, their accessibility today. They're not accessible to everyone today, right? On the right hand side for quantum bit, if you look at it, right, these are the output is usually generated in the form of histograms, right, or in the form of PDF file, or in the form of probabilities. So that is where we need to consider the, our statistical tools to find out or consider the actual output, what is getting generated out of a quantum computing. And uh, and most frequently occurring sample could be the answer. That is where we talk about mean or the mode or the median could be the most possible answer that could be, considered. The next section we'll just talk about quantum computing and artificial intelligence. So here, the power of qubits and AI combined, right? So till now we have been talking about quantum computing. Now look at how it is, paving the way, the breakthroughs in machine learning algorithms, in neural networks and large language models. So that is the power of quantum AI, or the qubits and AI. That is what we call about quantum and computing and machine learning. When we bring them together, there is a new term that has been coined, which is called it quantum machine learning. A new set of algorithms are being developed as part of quantum machine learning, right? So it requires new capabilities, uh, 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 right? And the way this quantum compute machine learning works is we should be writing quantum algorithms for performing those machine learning tasks, because see, not everything what works today, those algorithms, they will work for quantum, for using the quantum computing concepts, right? And utilizing qubit superposition and entanglement for computation is what would fall into quantum machine learning. It will, as I said earlier, it will enable solving the previously unresolved or intractable problems that we have been trying to do through. Then quantum machine learning algorithms, I'll just come to that, is there can be basis the data type and algorithm types. Those can be defined as quantum inspired classical algorithms on classical data, right? That is where some improvements or studies being done today, or companies like IT giants like TCS, Infosys are actually working in this area, right? The other could be classical algorithms applied to quantum data, or it could be quantum algorithms applied to classical data, or it could be quantum algorithms applied to quantum data itself. So that is a whole set of algorithms that need to be reconsidered today. Or as I said, the fourth one, quantum algorithms applied to quantum data is something very very not very difficult, but it's quite because of considering the limitations and challenges today. It's a bit tricky to actually develop and deploy. So we should actually be starting with quantum inspired classical algorithms on classical data, or the other two, right? Classical algorithms applied to quantum data. So that is where we are actually making a headway. And then there are typically some of the quantum machine learning algorithms that have been developed. Are some of them are quantum support vector machines, or it could be they work is actually classifying the label data, right, using quantum algorithms, or it could be quantum principal component analysis, right, for data compression and feature extraction. It could be quantum neural networks. Basically, again, quantum neural networks is similar to classical neural networks. It consists of just like classical neural networks, it consists of interconnected nodes or qubits that process and transmit the information. But in this case, instead of using the normal activation functions, they are using quantum gates to manipulate the qubit state or performing those computations. So qubit gates have already been spoken about, and one such qubit gate which QNN uses, quantum neural network uses, is quantum Fourier transform, and it allows for efficient representation, right? The data is actually represented in a frequency table, or as a frequency form, which allows for faster processing and better analysis of the data, right? And if we look at when we want to combine the quantum computing with neural networks, we could say that this quantum neural networks, they have this potential to actually tackle the most complex problems, which could be image recognition, or it could be natural language processing, or it could be optimizing the task more efficiently. We'll talk about this something when we talk about the applicability in the next set of slides. And the last one is variation quantum algorithms. So this is not a complete list, it is an illustrative list. Just wanted to put it over here, right? And with this, what we could achieve is key benefits in terms of exponential speed up, right? There could be lesser training time, there could be faster processing of data sets, there could be quantum data representation, right? More complex network topology, right? And there could be enhanced optimization in terms of automatically adjusting hyperparameters. We'll see that in most of the supply chain problems, right? Then complex problem solving. They are, if you look at quantum algorithms, so they could be used to solve the most complex optimization problems. And then handling the big data, get to the true objective, right? Being accurate, making those precise, accurate predictions on time, right? So that is what the power of quantum machine learning is all about. And it could power the future of everything, if not now, but at a later stage. We are still evolving. Working with quantum AI, as we see that artificial intelligence, before I talk about working with quantum AI, the steps, how does quantum AI work? Let us look at artificial intelligence, how it works, right? It is actually nothing but simulation of human intelligence by machines, right? And it's not a new concept, right? Its capabilities have been growing exponentially with the way our neural networks have grown, or the machine learnings have advanced, right? Uh, so today's AI can process data at large speed, right, and with great accuracy, and it can mimic or it can copy a human brain, and even I should say much better than a human brain. But what if we were to combine uh, quantum computing with AI, right? And that is inevitable, right? That is going to go through, and it's already beginning. So quantum computing, it processes the speed of processing capabilities, right? So AI will be the way we process our AI data sets, right? Or the way the time it currently takes to process, let's say, forecasting in a supply chain, or in a processing the IoT real-time IoT data, let's say in from freezing devices on container ships, right, or on the railroads. So the way it does is, right, it is going to exponentially change, right? It's going to be speeded up so that it could allow to, make those complex decisions, right? Analyze those vast data sets and make those complex decisions in a much real time. So that is what uh, quantum AI is all about when you want to talk about how quantum computing will work with AI. Now, if you look at this, just think of combining this computation power with pattern recognition, right? Now, when we talk about quantum AI, what if you are giving this computation power to artificial pattern recognition or learning capabilities of the artificial intelligence? The result could be significant, right? It could be humongous, right? We could get those ability to analyze vast amount of data, recognize complex patterns, right? The level of accuracy that was previously considered intractable at a much faster speed, right? And that is what quantum AI we are talking about here. Now, how does this work? So this works by preparing the quantum data, right? The data that you have, specific data into a language where it can be fed into the AI readable, right? The second one is processing that data using quantum neural networks, right? Unearthing or extracting that, mining that meaningful information. And then third is converting it back to readable formats for traditional AI. Fourth is again feeding this data format into AI, combining with deep learning and identifying those patterns and understanding the relationships, right? As well as predicting those outcomes. The fifth one is actually improving the AI itself, where basis the data that is processed, a sort of learning is going on, right? The sixth one is faster speed with much more complex data that we are going to achieve. And seventh one is deploying the quantum neural networks that we just spoke about in the last slide, right? So that is how the quantum AI will work. Applications of quantum computing in AI, right? So if we look at quantum AI, we have spoken about qubits, we have spoken about AI, we have spoken about quantum machine learning, we have spoken about quantum artificial intelligence, right? The transformative potential is actually extending to virtually every industry, right? And what we see that quantum AI is the powerful fusion of computing and artificial intelligence. The important thing is that it's generating a traction, right? It's confidence, a skepticism among the industry leaders, or the industries, or the academia, or the tech giants to venture into this space, right? So if we look at uh, it, if we look at the possibilities that it could do, it could solve complex problems, as I have been speaking about till now. That, well, at speed, uh, where our classical computers will just look like absolutely useless, right? Or uh, inefficient, right? So, but what's particularly exciting right now is, tech giants like this technology is actually becoming accessible. Our tech giants like IBM, Google, Amazon, and Microsoft, they're now offering quantum computing as a service, right? Till now, it was only available to very few academia or research institutes, right, or in the research domain. Now, business and researchers can actually tap into the power of quantum computing without having to build and operate their own quantum hardware. And if we take IBM as an example, they are offering what is it called as Qiskit runtime, which allows people to actually develop and deploy the quantum algorithms, right? So it's basically a way that's allowing every organization of all sizes, uh, everyone to actually experiment and potentially benefit from quantum AI capabilities, right? And a number of important ideas and prospective algorithms have surfaced till now, right? Even though quantum computing is still developing, right? And useful quantum algorithms are still being analyzed, researched, right? Let us look at a few of the worthy use cases that we could look at. If we look at life sciences and healthcare, what quantum AI could do, it could lead to drug discovery. It could lead to identification of molecular proteins that never existed before, or where our classical computers actually failed to do it right. So that is one area. The other could be uh, it could be looking at the profile of a patient or person, right, and identifying or leading to early diagnosis, right, or even to early discovery of diseases, right, or medicines in the life sciences and healthcare area. The other is actually, let's say, if we look at space and extraterrestrial. So NASA had actually done some research using quantum computing, where they had deployed quantum algorithms to find out the near Earth environment or a planet in this extraterrestrial system, right? And similarly, finance, if we look at, so creating those parameters, right, quantum computing can help analyze those parameters, right, where it can help investors to actually do their portfolio optimization and risk management, fraud detection, right? And similarly, in the case of energy, we could look at smart grid batteries, oil exploration, optimization, and sustainable energy. It could be using, for example, using hydrogen to build the steel products, right, or manufacture steel. It could be clean manufacturing, it could be clean energy initiatives, or it could be sustainability initiatives, right? In the area of transportation, we could optimize the traffic flow, right? Because as the vehicles move, a lot of data gets generated, and there's a lot of things that need to be done in real time. A lot of steps that could be taken in real time could avoid those exceptions and delays, right, and losses. So if I take the example of food industry, a lot of food gets spoiled on the way, right? And for this purpose, refrigerated containers have been brought into, right, especially on the vessels itself in an ocean. But uh, still, we feel that there is a need of, while the data is coming into the systems, right? Still, we feel that what quantum computing can do is speed up that entire processing and send out those messages to all the people on board and onshore and offshore, right, to take those appropriate steps to prevent those spoilages and damages. So there are many use cases, right? It could be in the defense state, it could be in the material science space, like identifying or looking at those materials which have not been fathomed or thought of, right? With that exceptional computing capability, can we think of actually sequestering carbon from the environment, right? And similarly, in the manufacturing and supply chain, how do we do more accurate forecasting, right? There is a huge focus on sustainability, right? So either you are short of demand or you are short of supply, or you are excess in demand or you are excess in supply. How do you do that accurate forecasting? So that is, we need to look at how quantum computing can actually support that, right? Or can be used in manufacturing and supply chain to make accurate forecasting. The other one is again cyber security, right? Basically, it's more about making more encryptions more better, while the information is communicated. So if we see that there have been many cyber attacks, and the recent one happened within the last 1 year. What is it that quantum computing can do to prevent those and improve those encryption mechanisms so that these sort of incidences can be avoided? So a lot of research work is being done in this area, and in fact, TCS has also partnered with many academia, many institutes, ISCs, IACR, IITs, and even with tech giants to explore the usage of quantum computing. And when we talk about challenges and limitations, so we see that as quantum technologies are advancing, we can expect quantum computers to collaborate with AI, right, to solve those problems uh, which were considered uh, unsolvable, right, or impossible. But if we look at the current situation, right, there are significant challenges that this field is facing, right, and it could be in terms of uh, scaling quantum hardware. It could be in the error correction, as I said. Error correction needs to be improved. So, as I spoke in the entanglement and superposition, uh, this error needs to be controlled, right? Any small variation in temperature or nuance or disturbance can lead to very significant errors, and the need for specialized quantum algorithms, right? And these computers function differently from traditional computers, right? So the way we are looking at the information in the terms of qubits, those algorithms must need to be rewritten from scratch, right? So we are looking at a vast possibility out there, right? But that is what we is something that needs to be looked at. And as I said earlier, these are very sensitive to environment, and even small disturbance can cause the errors in the computation. Uh, I think there's a limited, as I said, limited availability of quantum hardware, which it makes it difficult to test and validate quantum machine learning algorithms. So yes, as I said, uh, the infrastructure is very less. That the investments, the research is actually being done. The infrastructure, as I said, it could be in the form of cloud computing as a service, right? It could be the cloud services connected to this quantum systems, right? Quantum computers is one such possibility which IBM and other giants have taken, right, a step into, where people can actually explore. But yes, this is right now a challenge that the hardware is limited, right? It's quite expensive. Nobody wants to actually test it first, right? So that is where quantum computing as a service is coming into picture. Then these are not yet practical for real work, right? As I said, still the algorithms need to be rewritten from scratch, or a lot of research work has to be done. But yes, for the applicable use cases, right, these all of these algorithms are useful and all, unless we apply them to the real life use cases, right? So proper investment, mindset, research needs to be done, and how we are actually going to deploy these algorithms and for what use cases, and navigating the ethical and societal implications. That is what, who's going to use this technology, who will have access to it, can it be misused, can it be used for surveillance, what will be the ethics, what will be the guardrails. But yes, this is something that need to be done. But nevertheless, we see that there is research and investment in quantum AI that is rapidly increasing, and with the academic institutions, tech giants, and startups, they are actually contributing to the progress. And the next one is the road ahead. So as we go on, right, so we see that despite the challenges that we have spoken about, the possibilities are exceptional, right? There are a lot of vast possibilities in the quantum computing space, right? It could be better to call it as quantum AI, right? Quantum artificial intelligence. So So we can't just ignore it, right? We can't just say that there are huge challenges and we should not do anything. But rather, it's about, it's also not about just being having those faster computers or efficient algorithms. As I said, quantum computing is more about how we approach the problem solving, right, across all domains. I just showed multiple domains: life sciences, healthcare, space, defense, right? How do we deploy, or what are those use cases where quantum computing could actually be used, right? So that is where we should fundamentally think about, right? It's the challenges will ultimately be solved. Every technology comes with its own nuances, right? But it is the use cases part that we need to look at, right? And more importantly, it's about unlocking solutions to those problems which we were still not able to solve, right? With that exceptional speed, with that exceptional processing power, right? What is it that we can do? And as we see that the research continues to grow, develop new algorithms and build new powerful quantum computers, we can see that significantly there will be changes in the coming years, right? And we could see changes in the terms of quantum hardware advances, where there will be scalability. So currently there's less scalability compared to classical computers, right? It is less available to people, right? Nobody wants to own that hardware right now because of the infrastructure requirements. As I said, it requires very ultra cold environment, right? And has a high scope of errors. There would be new algorithms that will be coming up, right? So there are new art of possibles, new possibilities. There will be quantum native ML models that will be coming up. There will be hybrid models. As I said, it could be cloud applications connected to uh, quantum systems, right? And then similarly, they're being synergized with classical computing systems, right? In order to make the better use of both the environments, right? It could be broader applications in terms of climate modeling, right? How do we predict the climate, and what is it that we can do to prevent those impacts or catastrophes, right? And what is it that we can do in robotics, right? So what is it that with that now this quantum computing coming into picture, the natural language, pattern recognition, uh, right? All of that coming into picture with quantum computing. What is it that we can do to robotics? Can they be made more human, right? But it comes again with the drawback that being, I think, let's not talk about it. But it's how we can improve those robotics and right. What is it that these robots can do in our environments, right? For example, our warehouse, right? To store the inventory or to ship the inventory. What is it that quantum computing can do to those robots operating there? And then autonomous systems, yes, definitely. Tesla is operating the autonomous vehicles, and Uber has also tested the autonomous trucks. What is it that quantum computing can do to those autonomous systems? And then standardization and frameworks, that is definitely a need of the hour. What is the regulatory agencies the governments need to bring into picture? And lastly, the businesses need to consider those use cases, what they need to do, what they need to consider to efficiently utilize the quantum computing technology. So that is what I had. I think for this presentation, uh, I'm just open to questions now. So my role is more of, as I said, domain consultant. I look at use cases not just in quantum computing, but across multiple industries, multiple domains, multiple technologies, right? And then work with technology teams to get those developed. So I hope that I have been able to meet the expectations. If not, please, you can just make a mention. And I'm open to questions now.
Definitely, sir. Pawan sir, are you there?
Yes, sir.
Dr. Pawan?
Yes, sir. Participants, if you have questions, please use the chat feature and we will address them during the question and answer segment.
Please share the feedback form also, sir.
Okay, sir. Okay. Thank you everyone for your active participation and engagement in session 2. A big thank you to Mr. Ashish Tyagi sir for his insightful presentation on convergence of quantum computing and AI.
Thank you.
Thank you, Tyagi sir.
Amit ji. So I think I need to stay or I can just drop off?
No, sir. Thank you. Thank you so much, sir. Thank you.
Thank you. Bye. Bye everyone. Bye.
Thank you, sir. Thank you, sir. Pawan sir, please close the session.